Alright, so I'm going to start some math lessons here, and I have a ton of computer paper. So, I don't know, I kind of have to do math lessons on it. So, I'm going to start with an important distinction, an important thing we should instead teach in our schools. That really isn't. And it's kind of a simple idea that I'm trying to get across. And by the way, this is going to be one of those videos that gets deep, like a little fast. But either way, let's just start here. So I think the two important things to understand are abstract forms of teaching things and versus the big VS. And then, well, not abstract in this case, we'll have complex. And I don't know, we teach a lot of things aiming for complex. Like this, I don't know, this is the idea that we like to go for when we teach math. And I don't know, let's start here. Yeah. So this is how we kind of teach math. So first things first, we try to get this concept of number of, I don't know, usually I think like counting. I haven't really seen it any other way when I was first learning numbers. So let's use 5 as our prime example. So 5, that's just 5, 6, 7, 1, 0. They're all whole numbers. I guess you have this idea of 0 as a number. Some people might dispute this, but I don't know. 0 is kind of this concept that didn't exist in mathematics for a long time. And so the fact that we can have 0 is kind of interesting in itself. But either way, this is slowly getting a little more complex, but it's not that complex yet. After a whole and zeros, I guess we have like fractions, so rational numbers, 5/4. Just using that 5 idea. And that would introduce us to the rational numbers, just fractions of a number. And after rationals, I guess you'd have, well, the opposite of rationals in a sense, irrationals. And there's a ton in this category. Technically infinite, but I mean just like the idea of irrationals. So you can have irrationals like square root of 5. You'd have like the logarithm, natural logarithm in this case of 5. That wouldn't come out very clean. What else? I think that, oh, how about like pi and e and there's all sorts of other constants. You could have like the golden ratio, which is in itself a square root mixed with the rationals, but in the end, it's all irrationals. And I don't know, they're kind of hard to understand. If you only understood numbers as counting, this just getting to irrationals would be way too far already. So if you had a whole number, so like 5, I don't know, that makes sense. That's 5 items here. 0, no items. Like, that kind of makes sense. Oh yeah, and I forgot to introduce one other one that we like to talk about. Negative numbers. There's negative sets in all of these. You can have negative whole numbers, negative zeros. Well, no, you can't. But negative rationals, negative irrationals. Just put negative from any of these. Then, oh, wow, it's a negative irrational. Crazy stuff there. Either way, so we have negatives. And this is kind of the problem we start to reach. Anyway, let's stick with rationals for a second. So we have 5/4. So let's draw quarter dots. There you go. Totally 5/4 dots. I mean, they kind of look similar. Just accept it. Yeah, 5/4 dots. Good. That is a quarter dot. So yeah, 5 of them. Yep, works out perfectly. Just perfectly. 0 dots, 0 quarter dots, 0 whole dots. I don't know. Whatever measurement. Irrationals. I don't know. I can't give up now. I mean, you could have like 3 dots. A tiny bit of it. That doesn't look like pi, but it's kind of supposed to be. Let's switch colors here. Negatives. How do you even have negative dots? I don't know. I want to give up even more when I reach negative. But the problem with teaching complex is you can still go more and more complex in your like middle school and high school learning and stuff like that, but just gets off the wall because now you have like square roots of negatives, and then you have this whole idea of imaginary numbers. And if that wasn't enough for you, like we can't even like visualize negatives very easily. If this is your only system, just counting, it's awful, I guess. Imaginary numbers. Oh, and then even worse. Let's add like 5/4 to this, and here we have what we call a complex because you're mixing imaginary numbers with real numbers. So these are all real in that sense, but how do you even visualize both as counting? I don't even know, actually. I mean, there's probably a way, but what's even the point? If you have trouble visualizing negatives, you're gonna have a lot of trouble visualizing imaginary numbers and stuff. And even worse, infinities. How you have infinity dots? That's just ah. And then you have like 1/infinity, which is in a sense zero, but it's just then you have like infinities. And there's different kinds of infinities, but that's not what I care about right now. That's just more and more complex. And we're kind of built. The problem with teaching things getting more and more complex is that if you don't start somewhere solid, like just counting numbers, as you see, counting hardly even works for zero. Rationals, I guess you can count if you drew full circles and then cut them up like this. That'd be a quarter, and that'd be a quarter, kind of. But that's not even good enough. Like, we just teach in this path of complexity, and there's few ways you can teach if you don't have this solid grounding of something other than counting. I mean, counting only helps you in like whole integer numbers. By the way, these are integer in the integer set, same with just -5 and -4 or whatever. All positive and negative integers. That's just concept in itself, and I don't know, I just don't think it's strong way of teaching numbers in this sense. And I think there's a better way, and it's on the other side of this paper. Abstract. Slowly, when you teach math, slowly get more abstract. That's what I think we should do. And don't even start with numbers. I mean, like, when you start with numbers, you're confusing someone from the get-go. Like, who decided to start with numbers in the first place? I mean, it's kind of known. Like, we invented them for, like, money way back in Babylonia and stuff like that. But we don't really show that in our class. We're just saying, okay, you can kind of count things like sheep. And here, let's draw a sheep because I feel inspired. That's a sheep, by the way. Yeah, and do they have ears? I'll just say they do. Yeah, that's a sheep. Anyway, so you can count sheep, pigs, I don't know, count anything. And that's how we start teaching. And then I don't even know how they expect people to understand this. Anyway, let's go to abstract thinking. Let's not even introduce numbers when we're starting to talk about numbers. All right, let's start with like 5 items. You could have 5 nickels in your coin purse or whatever you store nickels in, even though they're not all that useful. But either way, so you have 5 nickels. You just have a set of nickels. You have a grouping of it. And there's a distinction here between 5 and 4. How do you distinguish between the two? I don't know. Wait, what if I had like a bunch? And by the way, when I say 5 and 4, I'm just saying it because you already know what numbers are. But in a general sense, when we first came up with numbers, we didn't really have a good way of distinguishing this. We just said that this set was less than that, this set was less than that, and we didn't even like write this lesson symbol. We just understood, hey, there's more stuff here, less stuff here, less stuff here. And so you can set up these inequalities, and I don't know, just a little weird, but we didn't really have ways of counting things. However, by introducing numbers, you can actually say that there's a difference between these 3 items and not have to worry about always saying greater than, less than other numbers, and always comparing. Because if you're always comparing, you're going to waste a ton of time comparing when you could just have numbers represent these like concepts. So you have 6 here, you have 5 here, and you have 4 here. Am I right? Yes, I am. And it's just by definition that 5 is less than 6 and 5 is greater than 4, either way. So the numbers are really useful for that scenario because they're really easy compared than this. I mean, after you start getting like in the 100 range of dots, you're not going to have fun counting these. So we kind of need a better way. This is okay system of counting, but there's other things we can do with numbers other than counting. You can also measure. I mean, way back in the day, we discovered pi because we'd sell like circle plots of land, which have if you already studied it, pi r squared. So whatever the radius is, area. And we'd treat like pi as about 3 or something like that. But either way, it was measurable. And so we get away from this idea of whole numbers and straight into this idea of measuring numbers. So this idea that you can unravel a circle from its radius. That's kind of like the radius length right there. And you have the circumference would be about 1, 2, 3, and then a tiny bit. So I guess I kind of went going over there. Either way, there's this idea of measuring numbers, and we actually thought these were completely separate ideas for a very long time. The Greeks kept on trying to combine these ideas because we understood things like the Pythagorean theorem. But like answers to it, like the most popular is probably 3 squared, 4 squared, 5 squared. That works out perfectly, and it's just whole numbers. Now there's other results, like if a and b were both 1, then this would have to be square root of 2 squared in order to work out. And we didn't like that. Irrationals. We just couldn't accept that for the longest time. And I think the fact that we teach math and we didn't show people that they couldn't accept certain numbers shows us that, like, oh, you're just supposed to accept all of this information and not understand that there was a time in history where we didn't accept 0. Yeah, none of it. Rationals kind of, we liked rational in Greek times and stuff like that, but irrationals, yikes, that's scary. And so we have this whole distinction between geometry and and we basically call it the opposite and say algebra. And these whole ideas completely split apart. The moving around of numbers, counting, and stuff like that. And geometry, just totally separate ideas. They are not equal whatsoever. No relationship. It wasn't until like 1600s when we started to reconnect these ideas, but that's aside from the point. We want to just start getting more abstract. So this idea of measuring numbers is actually really useful for understanding many of these things. So 0, it's this idea that you have no items. I mean, that's actually really useful because then when you have no items, you can multiply by no items. If you have no items, how much will you have after one day? If you get 5 times that number of items you started with, that's kind of a weird example, but you'd have 0 still. So it's kind of this weird number that keep multiplying, keep getting like 0. I don't know. It's a useful concept though, because we always encounter it in any measurement system. Temperature wouldn't exist without some 0 point that was important, and there's different temperatures, but that's getting off topic again. Anyway, let's stick with measurement and introduce these concepts along the way. So rationals, you could have 5/4. So if you had these were units, so a quarter of a unit would be about here. 2 quarters, 3 quarters, 4 quarters, and interesting enough, if you notice, 4 quarters lands right on 1. And in that sense, they're equal. So that's an important thing to understand. Let's switch colors again. All right. And then 5 quarters would be somewhere right here. Just 1 quarter away from here. So this whole length right here would be 5 quarters. And now it makes perfect sense. You don't have to worry about drawing these circles as fractions of each other. You don't have to draw a full circle and then part of a circle and say that, okay, this all together is 5 quarters. I mean, it works, but this idea of measuring is really useful. And so I think out of this, I mean, irrationals also work here. Like square root of 5 is a little greater than 2. There's a 2 here. So if you want square root of 5 on this line, give me a sec. Square root of 5 would be somewhere like right here. I'm going to going to guess. Now you have this length of square root of 5, and you have a perfect way of visualizing it. It makes perfect sense here. And I mean, this idea of square root of 2 being like the answer to this 1 by 1 triangle, you have already, if this was one length and one length, this would have to be irrational. So you actually encounter these things in reality. In fact, you encounter them way more than you encounter whole numbers. So this idea of measuring, I think, is a really important step into abstracting ideas. And so let's imagine an infinite measurement system. And in simple terms, it's called the number line. It sounds boring, but it's actually really helpful, because by moving it past the 0 direction, you can have an endless amount of space here, and you can visualize the numbers along it rather than just say there are these numbers and you can count them. This idea of measuring is really useful because, I mean, if you just showed people this much, they'd think, you kind of have to extend it because you want arrows on both ends. You want a line, not a segment. You don't want to just start here and go on to infinity. I think that's, yeah. And by the way, we already have our idea of infinity. It's just way out here in the distance. And this would be like negative infinity. This isn't exact, but it's a nice way of talking about negative numbers. And so all of these ideas are visualizable, able to be visualized. There we go. And oh, that's nice. And let's keep going more abstract to visualize the rest of these, and then we'll end the lesson. So I have this filler paper right here so I don't ink everything. Alright. So let's go on with abstract. So measurement, what we do when we talk about, what were we last on? We have all these ideas, but now we have these ideas we want to get. And so you can keep on doing that, just make it more abstract. So this measurement system, it works in this mathematical reality. And so let's continue with it. So we had our 0, then we had our n. I don't know, n can be any number. This would be n, negative n, the same distance on both ends. And so that works for all of the main numbers up to irrationals and negatives. But how do we do imaginary? Well, by the way, just quick thing, that thing is the same thing as square root of 5i. So it's a length of square root of 5. But what we say is I is just another direction. That goes through 0. Pretend it does for me. Thanks. There you go. Yeah, definitely. And so we have our imaginary over here and our reals. And in a sense, those are kind of bad names for it, because like imaginary, they don't exist at all. But that's kind of misleading. I mean, whole numbers, do they even exist? I don't even want to get into that. I told you this would get pretty deep pretty fast, but either way, so we have a way of visualizing imaginary numbers as just another direction on this infinite number line. Then we can have infinite imaginaries and infinite reals. And even better, the idea of complex numbers, all we have to do is combine the two. So if you want ni plus n, if you want to combine those, so n is just a random number. It could be anything. So if you want that, you have a way of locating it. And you even have this like distance right here you can calculate. I'm not going to get into that. But if you're interested, that'd be square root 2 n. Either way. For the same reason that triangle. Whatever. So either way, now we have a way of visualizing imaginary number. And I think that's great because like it combine just by making another line, not only do we have a way to put imaginary numbers here, we also have a way to put complex numbers by just combining the stuff in this measurement system. This would be a complex number, it could be n anything, could be anything really. But the whole idea is that you have an I component and then just a real component. I'll put an R here for real. And I guess imaginary component, whatever. Very useful. Now, the only problem now is how do you visualize infinity? And there's many ways to do this, but I don't know, my favorite is not only do you just draw this line, you draw this zone. Just call it like the infinity zone, you know. Very, very cool. It's an awesome zone you want to be in. So you have this zone where you have a negative infinity because of the negative direction. So positive direction, positive infinity. Then you have a infinity I up here. Then a negative infinity I up here. And I mean, necessarily this is the stuff we care about because real numbers take it to infinities. The more useful sense, but I imagine you could have these imaginary numbers. So anyway, very, very useful for understanding these. And now we have a way of thinking about all sorts of numbers in a way that's better than just getting more and more complex. Because if your system isn't strong starting out here, it's not going to get any stronger. So we want to get more abstract. We start with this idea of counting. We move on to this idea of measurement to find areas and volumes and stuff like that. Then we move on to this idea of geometry and algebra as these two different ideas altogether. And it just keeps on going on. And then we have this idea of a number line. Number line extends into this imaginary real plane. It's two directions, so it's called a plane. Just interesting. And then three directions would be like a 3D space. It'd be a space, I'm pretty sure. And going here, I don't know, it's just another way to put infinities out there, even when they aren't usually put there. Anyway, so now we have a way of visualizing all of these abstract ideas. And if you have more numbers that you invent, what you do, and they don't fit on this line, what we do is we just take another line and jet it out in the 3D direction. And now we have a way of visualizing these things that are not imaginary or real. Just getting a little more abstract, but it is measurement in its own sense. In fact, that's why I think numbers should be considered just a system for measuring. System for measuring. And I think all of this is pretty deep. I mean, I might like math, so that's probably why, but I don't know. I think it's pretty interesting to think about math in this way of getting from complex to abstract. Yeah, and so we should change the way we teach from complex thinking, getting just more and more complex with a weird starting point, to abstract thinking, where you actually put measurement on things, where you actually put this idea of abstracting things more, making them not more complex. In an essence, it becomes more complex because you have more things to care about, but more abstract things don't necessarily have to be complex. You can visualize numbers as counting still, but there's just many ways you can visualize things. And abstract, I think, is about making more ways of visualizing things. And I'll end this here. Thanks for watching.